Okay, everyone. We're still technically 2 or 3 minutes ahead of schedule, but since we have pretty much standing room only already, I think we might get going. And I should say that the only other person I can think of who would create a standing room only buzz probably is will.i.am, who of course is coming tomorrow night. And you're all warmly welcome if you haven't yet signed up for will.i.am, who's going to be talking in the chapel, not about music, but about the work he's doing to use AI with the University of Arizona to try and reach underprivileged and excluded groups for education. It's a really interesting project he's involved in, and King's is incredibly proud of being engaged with a lot of initiatives to do widening participation, WP, for students. And so I'm really excited to hear what he's got to say about that. But before that, let me introduce somebody who's actually worked with will.i.am and many other people, who is James Manyika, who I've known for many, many years. By the way, I should have said at the beginning, for those of you who don't know me, my name's Gillian Tett, I'm the provost here. I did a PhD in Cambridge, then went off to journalism for about 30 years, and then came back a couple of years ago to be here at King's. And I first met James when I was just a journalist, just a columnist, and he's had a fascinating background. He originally did a PhD in AI studies himself, not at Cambridge, but at the other place, Oxford, boo, and was actually at 3 different colleges, and I believe is still associated with All Souls, I believe, yes, Keble and Balliol. Then went on and did a variety of consultancy projects, worked at McKinsey for many, many years, which is where I first met him, where he did some fascinating work on modeling the global economy and business and its interactions with tech and the environment and other themes. And then, I think it was 4 years ago, you joined Google, where he now has a job description which appears to change every 2 minutes as Google changes and as DeepMind came in. But roughly, I think, means he's in charge of 2 things. One is a lot of the AI research, you can correct me in a moment, and secondly, in trying to explain what Google is doing and DeepMind are doing with AI and quantum is actually taking up a lot of his time, and how that interacts with governments and societies around the world. And as part of that, he co-headed a commission at the United Nations, which was set up about 18 months ago, if I get this right, to look at how to create intergovernmental policies on AI, which achieved something quite remarkable, which appears to have been the only joint declaration that both America and China signed together. So he's clearly got great diplomatic skills. But he's got fingers in many, many pies. Over the years, he and I have done a bit of brainstorming around issues of AI and trust. I've been bashing people at Google over the head for a long time and telling them to hire ethnographers and anthropologists. I'm a sort of job creation scheme for anthropologists, because I used to be an anthropologist myself. And I'm just absolutely delighted that he's here today to talk to us about the work he's doing and his thoughts on this. As all of you know, this whole event has been set up by Stephen Cave of the Center for Future Intelligence and a whole gaggle of people who've worked insanely hard to make it happen. And it's just wonderful to be here today. If I had to change one thing today, it would be to actually obviously keep the statue of Keynes in the corner, who looks thoroughly grumpy, but then add a statue here of Alan Turing, because the reason we're here at King's today is because just across the courtyard was where Alan Turing lived, did so much of his work. We've just come from the archives, which have a lot of his amazing material over the years, and we're incredibly proud of that legacy and very determined to make sure that that's a strong platform to look to the future and imagine how AI is going to impact us all. So, James, no pressure, over to you.
First of all, thank you, Gillian, for that overly generous introduction. And it's wonderful to be here. It's wonderful to see all of you. And it's also great to have spent the last sort of hour in the archives, seeing the extraordinary papers, writings, letters of Alan Turing, and perhaps the reason all of this is we're at this exciting moment in the development of intelligent machines, I think, as he called them in his work. And thank you for the invitation to come be part of this at this 75th anniversary, I think, of the Turing test. What I thought I would do is to maybe speak for about, I think I was told about 20-ish minutes, and then we're going to have a conversation. And what
and then welcome questions from the audience, by the way, as well. You'll all have chances to ask questions.
Yeah, no, I thought what I would do is to maybe go through the remarks around 4 questions that I'll try to kind of walk through, and I'll try to signpost them as we go. The first question is, what has been the aftermath of the Turing test, since that's the kind of the moment we're in? Well, the Turing test itself, I think, bears no description. I think most people know what it is. And it's always been a very fascinating thing. But I think one of the things that has always struck me was if you actually read the paper, and I was actually delighted to actually see the original copy of the paper just before this, my favorite part is actually the end section. Because one of the things that Turing did in that paper is he anticipated 9 objections that people were going to have to his paper. So he kind of preemptively debunked all of them, all 9 of them. So if you haven't read that part of the paper, please do. Some of my favorite objections that he actually highlighted, one was what he called the heads in the sand argument. Where he basically, he literally titled it that. He meant people were going to have their heads in the sand about the possibility of intelligent machines. And so he had a whole argument of why he was going to refute that argument. The other one was, that I also like as one of my favorite, is the Lady Lovelace objection. This was based on the argument that, well, machines can't really be that creative. So Lady Lovelace has actually talked to him about the possibility that machines could never be creative. The third one that I actually like is what I'll call, he didn't call it this, but I'll call it the Gödel argument. And this was probably the one that sounded quite serious in the sense that it was based on kind of the incompleteness theory from Gödel's work, and the argument that in fact, because you couldn't actually have a fully Turing machine because of the incompleteness of the Gödel theorem, so this was never going to work anyway. So this actually arguably was going to refute what Turing had to say, but of course he argued against that too. So anyway, it was fascinating. So if you ever go read the paper, read the back section. It's actually wonderfully written. But I think the one thing to note about the Turing test that I've always liked about it is what I call kind of the 2 key insights from it and the flaw in it. So the 2 key insights that I found fascinating was it was the first time anybody actually articulated clearly the distinction between what and how. Because if you think about how the Turing test is actually set up, it takes away how this is being done and mostly focus on what is being done. Does it look like intelligence? And I think that theme has stayed with the field for quite a long time, the distinction between the what and the how. And of course, some people have argued against that. The other key insight I think that he did was he basically made the test a disembodied test. Because papers are being passed back and forth, he tried to take away the idea of a body, a voice, gestures, kind of confusing the assessment of intelligence. And I think that's also stayed through with us to some extent. The flaw was interesting. He didn't actually highlight it, but many others did afterwards, which is there's an enormous amount of subjectivity involved in the test. Because at the end of the day, the evaluation is done by somebody who looks at it and tries to guess, and obviously that's very subjective, and that became a flaw. So if you look at some of the aftermath of the Turing test, whether it's the Chinese room argument from John Searle and others, it gets at this what and how question. How is this being done? And that's the essence of the Chinese room argument. If you look at some of the subsequent demonstrations, whether it's the ELIZA demonstration or even the Perry one, I don't know if you've actually read the Perry version of the ELIZA machine. The Perry has been described as kind of ELIZA with an attitude. And then even the Guzman demonstration, which was in 2014, which claimed to have done this. If you look at all those examples, they highlight the flaw, which is it's easy to manipulate the tests and take advantage of almost human psychology and set it up in a way that allows the test to be passed or failed. So arguably, that's been one of the flaws in the Turing test. But I think it's also worth noting that over time, a lot of other tests came up which tries to make up for some of these flaws. Whether it's the reverse Turing test or and a whole range of others. The one that I like is the Winograd schema challenge. Because one of the nice things about that one, and it's still very useful today, is it tries to take away the subjectivity in it and tries to also get at some very common sense examples of intelligence and understanding. It plays with changing words and in text and so forth and see if the machine or whoever's assessing can actually interpret what's actually being referred to when it's they or him or her or it and so forth. So it's actually been a very useful test. If you look at where we are today with a lot of these tests, the field when it comes to testing has moved on quite a lot in a couple ways. First, there's been an ever ratcheting up of benchmarks. One of the things that's been quite remarkable in the last few years to see how many more benchmarks keep getting ratcheted up, whether it's MMLU or GPQA or any of these benchmarks that are typically used to assess the performance of these models. Each time the machines or the models start scoring in the 80s and the 90s, somebody has to dream up a new test as the ratcheting keeps going up. But the other thing that's also interesting is, and there's been a bit of a fragmentation here, and I'll use two example current tests that kind of illustrate the fragmentation. One is, if you haven't come across it, is Humanity's Last Exam. I don't know if you've looked at that. What it is basically is it tries to source something like over 2,500 questions from expert level, almost PhD level questions in a variety of fields. And it's a very hard test, actually, because if you look at the questions in it, you can imagine one expert being able to maybe answer the questions in their particular field, but it's quite unlikely that any one person would ever answer all the questions in all the fields at that level of expertise. And it's the reason why this one's interesting, well, first of all, most models score very poorly on this, by the way, generally today. So it feels like there's still a lot of headroom in this one. But it's an example of a test that tries to get at intelligence as indicated by what you might call crystallized knowledge. So in other words, what do you know? What do you know? So it's a form of kind of crystallized knowledge. The other test that's actually useful to point out goes in a slightly different direction. This is the RKGI test. And what that does is less about crystallized knowledge, but more about what you might call fluid knowledge, or what you can learn and what you can reason through, starting with some very basic knowledge, but then work your way through things. So these tests are indicative of kind of tests going in two different directions. It may be that we need both, I don't know, but that's interesting. And in fact, recently somebody actually back in 2021 proposed the Nobel Turing Challenge, by the way, and we'll come back to that when we talk about science. But this is kind of where we are, which is, a barrage of tests, a barrage of evaluations, typically testing for slightly different things on this question of intelligence. And all of us and my colleagues and I, as you might expect, we spend an enormous amount of time assessing how well our technologies and systems are doing across these tests. And that's typically what you see in all these various leaderboards that people pay attention to and track all the time. Let me get to my second question, which is, given all of this, where are we in the development of the intelligent machines that Turing imagined? And is this any indication to progress towards the so-called, AGI, whatever that is? We'll come to that in a second. First on progress, I mean, it's been spectacular. In the last couple of years alone, it's hard to keep up with the incredible progress of these technologies and the development of them, at least at the research level, which doesn't always show up in products necessarily, because there's always, I think, a bit of a gap between what's being researched and developed versus what actually ends up showing up in the world. But you could easily say these models are much more multimodal. They can deal not just with text, even though the transformer-based architecture started with text. They're no longer that. They can deal with, text, voice, images, video, all of that. Maybe some of you have even played with some of our recent image and video models, Nano Banana being one that seems to have captured people's attention, and models like VO3. So the multimodality has made a huge progress. Progress has also come in terms of what are called these thinking models. You can debate, to what extent is that really thinking, as opposed to kind of making use of chain of thought reasoning and reasoning traces to try to elicit and get the models to ponder a little bit more or do a little bit more work before they come back. So you've got that. You've also got progress in terms of now agentic systems. So it's not just things in and things out, but systems that can actually start to take actions. And also the shift, not quite a shift, but the addition of not just things you can do at training time, but what you can also do at inference time with the so-called inference time compute. That's been fascinating. And now you're starting to see the next big push around world models, which are fascinating. So there's lots of kind of progress that way. The one thing I would say, though, is that some of the most impressive systems and technologies out there have tended to be, in recent times, more what I call hybrid systems. So I think it's easy to imagine AI equals LLMs. It's actually, the field is much broader than that, and people are using a variety of techniques around that to do lots of things. So if you've seen some of the systems that have done well, for example, in the Math Olympiad, for example, a lot of those are kind of hybrid systems. Sure, it may be using an LLM for part of it. It's using other techniques, Monte Carlo tree search, or even neurosymbolic reasoning engines kind of put together to do interesting things. So these are often very hybrid systems. On progress, one more thing on progress, I should also point out that the progress in AI has also led to progress in a few adjacent areas. So robotics is one area. So when I did my PhD, it was actually in AI and robotics. Robotics had kind of lagged for a long time, even though it had been making progress. But recently, with the so-called vision language action models, it's actually now possible to actually leverage and draw on the capabilities that we've come to appreciate in these foundation models linked to robotics. So I think you're starting to see bigger advances in robotics in just the last year alone, compared to what you might have seen in the 10 years prior. And then also in these robotic systems, they've also become quite real. I happen to live in San Francisco, and in San Francisco we've had Waymos running around. Gillian knows this, she spends time in San Francisco, for 2 years. And these are extraordinary systems. I mean, Waymos have now done over 100 million miles. If you're in San Francisco, a third of the paid rides in the city are Waymos. And so it's extraordinary to see for this form of embodied robotics in the real world, purely driverless and so forth. That's quite remarkable. But I should also say there's still a lot of limitations, despite the story of progress that I've been describing. There's lots of limitations. These include the fact that, often these systems are very inconsistent. Performance is very inconsistent. You also find that often they will hallucinate, although hallucination rates are coming down quite significantly, but they still do. You often find that some of the common sense reasoning doesn't actually quite work. They'll quite fail at, I mentioned Winograd schema challenges, and even those kinds of challenges to reason at things that any of us would do quite easily. And even in some cases, they'll fail to count properly, which is kind of surprising in many ways. And then you've got some other deeper challenges, because the ones I just mentioned, you can imagine making progress on those. Some of the deeper challenges include things like, how do you think about long-term memory, planning? How do you think about moving away from just statistically derived intelligence to more causally related intelligence? So there's some deeper questions that are still gaps in what these technologies do. And you might even link some of these limitations to the current architectures themselves. Other challenges with these systems, they're still, for all the things that we use in these transformer-based architectures, these are so computationally intensive. And it's one of the big challenges that's actually causing, for example, when you're using these transformer-based architectures to need so much compute, which then translates even into energy needs to go with the compute. These are things that I don't think anybody wants, and so there's more to do on that front. But you could ask the question, so okay, just with all this progress, and are we headed towards AGI or not? I think, well, first of all, it's worth actually talking about what is AGI. There's so many different definitions of this. But I think it's worth noting that AGI isn't something that my colleagues and people in tech dreamt up. I mean, this idea has been around for a very long time. In fact, even Turing had a version of it, although he didn't use that term AGI. Even the group that gathered at the famous 1956 conference had it. And in fact, I thought I would actually read how they described the summer project at the Dartmouth conference. In fact, it says, quote, "The study to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. And so an attempt will be made to find how to make machines that use language, form abstractions and concepts, and solve the kinds of problems now reserved for humans and improve themselves." So the idea, even though that term had not been used, it was been around for a while. I tend to like as a definition, what I think of as a common sense definition, which my colleague Shane Legg, one of the co-founders of DeepMind, came up with. Shane is one of the people who started using this term, by the way, AGI, in 2002. And in that, and what he basically described at the time was, it's a system that has the cognitive capabilities you'd expect a typical human to have. It's a very simple, common sense view of it, and I think it makes a lot of sense. But you could also argue that you could imagine a much more stringent, maybe even higher bar version of this, and this is often the way my colleague Demis usually describes this, which is closer to the Turing vision, because it's linked to what you might think of as a universal Turing machine, where you assume kind of architectural completeness, a much, much higher bar, being able to tap all the possibilities that are in principle possible. So with that definition, you might expect a much higher bar that might be a lot further away as you think about it. But I think it's worth realizing that all of these definitions are really on a continuum. And you might be hitting kind of a few milestones along the way. They're really on a continuum, to maybe eventually getting to what some refer as artificial superintelligence. But I think it's worth thinking back in the context of the Turing test. How would one even test for one of these systems or for an AGI? And one of the ways, at least, one of the examples that I like is actually one that my colleague, again, Demis, likes to use, which is, something that might give us a glimpse is, imagine if you trained a model with all the knowledge that was known up until 1905, would the system come up with special relativity on its own? If you could do that, if you had a knowledge cutoff, then that's interesting. Could you have a machine that would come up with, multiple move 37s from the game of Go? So I think we're starting to think about what might some reasonable tests be to know when we're in the threshold or close to AGI. One of the big debates, by the way, in the field, and we have it even amongst my colleagues who work in AI research at Google, but it's also emblematic of in the field. There seems to be sort of two camps. One camp that believes that, scaling and engineering will get us there. And so, we kind of know we have all the pieces. We just need to do more engineering work. And the second camp tends to think, yeah, that's interesting, but we're probably going to need a few more breakthroughs that we don't have yet, because it's not clear that simply pursuing the current transformer-based architecture and all these kind of autoregressive, way of, token prediction and understanding will get you to all the other things you need. For what it's worth, I tend to be in the second camp that, sure, these foundation models are interesting, but we're probably going to need a few more breakthroughs before we get to something particularly really interesting. Which gets me to my third question, which is, all of this to what end? One might ask, to what end? And here, at least, I'd like to describe the kinds of things that I think we think about, my colleagues and I think about, and what motivates much of what we do. And it's actually sort of in four parts for us. One is the idea that these technologies are going to be extraordinary at empowering individuals in their everyday tasks, their most ambitious, imaginative tasks, and the kinds of things that they would like to do. And at least in a think about humanity, one example that I think of a lot, and it's one of the things we work on a lot, is to imagine how this could be useful to everybody. One way we're trying to do that is through language and languages. So, think about what's in Google Translate. And if you think about it, if only you focused on the language that you think matter, that people like us speak, and you could imagine a commercial interest driving, you probably do 30, 40 languages maybe. Those are probably the languages spoken by people who are monetizable in that sense, if you want to use that commercial view. But in our case, for example, right now our current moonshot is to get to 1,000 languages, and we're already at 250. We keep trying to add to this. In fact, if you want to get to the languages spoken by most of humanity, you'd have to get to like 7,000 languages to get to all of them. So there's a lot more to do. So this idea of empowering people is one of the things that kind of motivate us and motivate many of us, particularly people like me who grew up in different parts of the world where they didn't have access to resources and knowledge. It's a very empowering thing. The second thing we think about in terms of to what end is the potential for this technology to actually power the economy and prosperity. The economists in the room will know that for the longest time, and you may have seen this in the current recent round of Nobel Prizes, innovation and technology has been the underpinning of much of economic growth and prosperity over centuries, actually. And at a time when we have productivity challenges, this is a technology that can actually help us make a difference. It has two key characteristics that I think make it particularly interesting. On the one hand, it's a general purpose technology, and we haven't had very many of those. General purpose in the sense that you can imagine all human activity that has any economic relevance being in any sector, in any occupation, in any country, across countries, benefiting from use of this technology. So it's a general purpose technology. We haven't had very many of those. But AI also has a second, I think, perhaps unique or relatively unique aspect, which is it's an invention for inventing. And I think if we think about these two aspects, the possibilities, I think, become enormous from an economic standpoint. So you've seen lots of estimates about the trillions of dollars of economic growth and productivity. I think those are interesting, but I think they're not going to happen on their own. They're not guaranteed. I think there's a lot more that's going to have to happen, and we can go into that discussion as to what would need to happen. But this potential of this being an empowering economic driver for economic growth and prosperity, I think is one of the motivations. I think a third one, which I think is not talked about enough, especially given the progress of the last few years, is the potential for this technology to actually advance science. And I think this has been phenomenal. And I think, what's amazing about this part is it's not just in the future, but it's already here. Obviously, my colleagues Demis and John got the Nobel Prize for their work in AlphaFold. But I think the thing that I find interesting about the AlphaFold example isn't, it's the breakthrough, of course, which is amazing, but the fact that we open sourced those data sets, and I think as of last month, something like 3.4 million biologists in the world in over 190 countries are using those to work on any number of things. I think that's extraordinary. So I think the idea of doing science at scale is one of the key features of this. AlphaFold is one example. Another example is one of the things we worked on called AlphaMiSense, where, for example, geneticists only understood these so-called genomic misspellings that happens in the genome, and there's something like 71 million of them known. And I think up until our innovation AlphaMiSense, only 0.1% of those had actually been sequenced. And with AlphaMiSense, we're actually able to do 89% of them. So this idea of doing things at scale. Material science is another one where we've come up with lots of new crystals that were not known to exist before. So the idea of science at scale is interesting. Another aspect of the science part is that this idea that we're giving scientists a new microscope to be able to look at things that they couldn't look at before. And we've seen this in our case, for example. We've had a 10-year research project at Google Research on connectomics, trying to understand the wiring of the brain. And using the tools from AI, we've actually been able to go to almost nanoscale level of understanding of at least a piece of the human brain, and we're extending that to a mouse brain and ultimately to bigger and bigger brains just to understand it. One that I think is kind of cool because it's a very recent one, the results were announced this summer, was from the LIGO, which is the interferometer, which is trying to observe gravitational waves. One of our AI systems, deep loop shaping, was actually used to be able to almost microscope in, be able to observe in the edges of black holes in ways that couldn't have been seen before. So the results of this were actually shown, I think, 2 months ago, which is quite extraordinary. I think the other way in which this helps scientists is the idea of a co-scientist, a tool that can actually help scientists do their work and explore different possibilities. And we've had quite a few examples, including, for example, systems that have been able to explore possibilities, for example, in drug repurposing, and found different uses of drugs that weren't known before, just because they searched everything and tried everything. And then the nice thing about this is you can actually validate them in the lab once you find them to see, are these actually working? And so through some work that we've been doing with Imperial College and Harvard and others, this has actually been shown in practice to actually lead to new solutions. So the idea of co-scientists is interesting. I'll give you a few other examples. In fact, there's one that we're announcing today. Julie will tell me it's not out yet. I think we've said it, which is using, for example, what's called a cell-to-sequence model to actually be able to predict and see different kinds of cancers and that in ways that are quite remarkable. I think that's going to be, the paper's going to be out today. So these are ways in which AI is actually advancing science in fairly extraordinary ways. And maybe the idea of the Nobel Turing Challenge will become a reality. This was posed in 2021 when somebody said, well, maybe we should wait for some day when an AI system can actually lead to a Nobel caliber discovery by itself. I don't know if that will happen, but what I know will happen is the fact that we're probably going to see many more scientists actually make discoveries using these tools in quite extraordinary ways. The last piece of what motivates us, just to finish this section off, is the idea of actually applying these technologies to actually tackle societal challenges at scale. And I think this is important because it's already happening. So this is not some futuristic things. I'll illustrate this with a couple of examples. One of the things we've known for some time is, particularly now with the huge prevalence of extreme floods and a higher frequency of them, it's always been known that if you could actually make those predictions with something like more than 6 days advance notice, you'd save lives in extraordinary ways. This has been known for a very long time, except that there's no reliable way to do those kinds of riverine flood predictions in any reliable way. So one of the things that one of my teams, Google Research, worked on about 2 years ago was to actually try this out and use an AI tool to do this, and it actually worked. This was in the southern part of Bangladesh. And now, I think we now cover something like over 100 countries with these flood predictions where more than 700 million people live. And I think that's quite extraordinary. We're doing the same thing with wildfire boundaries when wildfires happen to actually try to track the boundaries. We're doing this in 27 countries. And actually quite recently, a new innovation, which is FireSat, which we started, actually got one of the Time 2025 Inventions of the Year awards, is where we try to predict actual fires themselves. So we're putting up a constellation of 53 satellites. The first few have already gone up. And in fact, in July, they were actually using these AI techniques on these satellites that are up. We're able to actually observe a wildfire which no other existing mechanism would have predicted and observed from up in space. The constellation is incomplete. That's still going on. So you have all of these kinds of examples where the predictions, cyclones, actually a recent example from this last summer was we're now able to predict with relatively good accuracy cyclones and monsoons. So we actually teamed up, for example, this summer with the Indian government and the University of Chicago, and we're able to predict monsoons and get that information to over 38 million farmers in India ahead of time using these techniques. I illustrate all of these to say these are real things. that are already happening today, not in some far future where we're able to apply these technologies. I could have given you examples in health diagnostics is another key area where these tools are, particularly for people in places that don't have access to resources. I hadn't appreciated, Gillian, that, for example, something like 40% of people with tuberculosis in the world go undiagnosed because they live in communities and countries where the facilities and resources just aren't there. So we've been doing some work using these tools in Southern Africa and India to do TB diagnostics. So I could go on. But I think these are some of the things that motivate us as to why focus on this technology and what could it bring to the world. But it brings me to my final part of my remarks, which is, but given all of this, what is it that we must get right about all of this? And I think, and here, a few years ago, actually several years ago, a few of us came up with this thought experiment, which is, imagine it's the year 2050, and and we're all looking back, and AI has turned out to have been a wonderful thing that happened. And so the question is, what happened? What did we get right? What opportunities did we capture? What risks did we avert? What did we manage? What did we get right? So it's just a way to think about what are the things that we have to get right. And in a paper that I wrote, I guess a year or so ago, I sort of, from my point of view, but I'd welcome other people's view on this, your response to this thought experiment about what we have to get right. When I wrote this paper, at least I highlighted kind of 5 things, 5 categories of things that we'll have to get right if we're going to have this happy outcome when we look back from 2050. The first one is that we will have managed to build very capable AI, capable enough to do the things that we want to use it for, that benefit the world, but that's also safe, trustworthy, and that we've done that. Because if we don't do this part, the public won't trust it, society won't trust it. It also won't be doing the amazingly wonderful things we'd want it to do. So this is one of the things that, one category of things that I think we have to get right. A second one is that we actually have to, if we look back, we will have had to realize all these amazing things I was just describing fully. Because if we haven't realized this, if these are the things that are motivating us to do AI, but they haven't come about, that's a problem. So we have to realize the potential. We also have to realize and navigate it through the impacts associated with that potential. And that impact includes the impact on sectors, on jobs, on a whole variety of areas that, even though they may benefit from these technologies, are probably going to be transformed and changed from what they are today. So we'll have to have gotten that right. But the other key part of the second piece of, realizing the potential, which is perhaps the hardest one, is we'll have had to make sure that everybody's benefited from it. Because it's one thing to have economies grow, it's another thing to have all these things happen, but not everybody benefits from it. I think if we don't get that part right, and it won't happen by itself, I don't think we'll have that happy outcome. So that's the second thing. The third category of things I think we have to get right is what I would describe as the responsible development, deployment, and use and governance of this technology. This is a lot of what we worked on in this UN high-level body that Gillian was describing, which is how do we get the responsible part of this right? And I think it covers all the pieces. It covers the development of this technology responsibly. It also includes the deployment of this technology, because it's one thing to have technology developed one way, but deployed a different way. It also has to include the use of this technology. We all know the examples of lots of amazing technology that gets misused in any number of ways, misapplied, misused in any number of ways. And we have to get the governance of this right. And I think this is the really tricky, complicated part, especially in the world as it is. How do you get governance right? And how do you get responsibility right? My view is I think it's the responsibility of everybody. I think it's the developers of the technology, people like us. It's the users of the technology, the deployers of the technology. It's governments, it's policymakers. It's also citizens. We have to shape this. But this gets very tricky very, very quickly in ways I'm happy to describe it as experience on the UN high-level body as to where did we get to And that was last year, and the world has changed, right? So where did we get to at that point, and where are we now? And then I think the fourth area we have to have gotten right is, even if we get the other things right, is that there's perhaps a deeper thing that I don't think we're spending enough time on, although I know some of you are, which is, how are we going to deal with the co-evolution of our societal systems and what it means to be human in the age of AI? Because even if you have solved the risks and the complexities, we know that education systems are probably going to be different. We know that how humans flourish is probably going to be different, even if we get everybody to benefit. So there's a whole rewiring or adaptation of our societal setup that is set up in a very different time when we didn't have these incredible capabilities that we'll have to rethink. And I think in thinking that through, sure, we should do that with an eye towards what can be, not only what will be lost, but also what could be gained. I don't think it's a one-way trip. I think you have to think about both sides of that. And then obviously the question of what it means, to be human in the age of AI, especially at a time when, up until now, most things that we've ascribed to as being human properties and what's unique about humans, many of them, I don't think it's all of them yet, but many of them are things that will probably be able to be done by these systems. It's a bit of Turing's argument if you read the end of his section, and he was already prescient about this. This is what he called the heads in the sand argument, which he tried to refute in his 1950 paper. It's worth thinking that through. And then final point where we have to get right, and again here I'll link back to Turing, is the thing that Turing worried about, which is in 1951 in a couple of speeches and essays that he wrote, which is around the alignment question. Ultimately, and I think I'll read a quote here from what he said in 1951. He said, quote, "It seems probable that once the machine thinking method is started, it would not take long to outstrip our feeble powers. At some stage, therefore, we should have to expect the machines to take control." This is the alignment problem. So I think we're going to have to get this part right too. And I think this is a very important part of it. So with that, I'll stop, Gillian. Hopefully that's interesting. I'm sure we'll get into some of these questions.
Well, absolutely fantastic. Thank you very much indeed.